Okay, forgot to record this Pappus theorem. Anyway, so we get the volume of a donut by Pappus theorem easily. You can even have something that uh, more general. So donut with last radius, small radius. This is what I meant. This R, this is R. Okay. So this is a oh, okay. So the uh, radius is R minus R over 2. Okay. And this distance here traveled by the centroid here is just 2 pi uh, in general. So by Pappus, volume of this donut is the area. What is area? Area is pi r squared. This is radius. Okay, so we have 2 pi times so this distance times this area. Okay. So what you get here? Those two 4. All right, so let's see. This cancel. So this remains so pi. Okay, and here you have r plus big R, capital R plus small r is minus. So you get, there we go. That's the volume of this donut. Get the formula of this. Questions? Okay, so far? All right, let's continue with the next one. Is the another application in physics. It's work and force. We skip this one, so no. Continue with the force. Where is the next section? Hmm. Hmm. Oh, sorry. Turned out to be the previous sections actually. Sorry, this is should be the last one. Here. All right. Okay. So this is the okay. So this we have a formula here. Work is force times distance. Yes, from the your mechanics. So first chapter of your physics. So, okay. All right. So let's just do directly um, in pumping liquid here. Okay. So just to give you the idea and we compute that later. Okay. So for example, we are pumping you have a underground um, water reserve. Okay. Say the shape is a whatever, whatever the shape here, but it looks like uh, a box here, just a box. Okay. So let's uh, how do we do this one here? Okay, so the thing here is that we're looking at this part, this liquid here, has to travel this distance to the spout of the pump. Okay, while the part of the liquid here, water here, only traveled this distance, which differs quite significantly to the one at the bottom. Okay, so how you empty the tank here? Just pumping each layer of this, layer by layer. And we compute for each layer the work done by this force. Of course, this force is the gravitational force. Okay. So that means layer by layer means that we are doing partition. Okay. So partitioning the partition this one. So one layer is a sample. Okay. And we pump that layer. So we compute the force, the gravity force, times this distance. So this layer. So you have gravity force, but you have this distance. Okay? And for just for this layer, and for the whole layer, the gravity quite the same, except the distance is different. Okay? And you sum them up, and when you take limit, that's the integral. So that's the idea. Okay. So let's do this example. I'll do that in the um, This is the situation. You have a tank in the shape of a right circular cone, okay, full of water. If the height of the tank is 10 feet and radius to the top is 4 feet, find the work that's pumping water over the top edge of the tank. Pumping water height above the tank. Okay, let's see. So what's the so we have the tank, circular cone. This is 10. Okay, radius to top is 4. Okay. All right, so here's the pump. So for example, here's the pump and here's that's the spout. So this is pump here. So water comes out of this. This is water, full of water. So just look at A first. Later at we see that the B, part B. Okay. So what were we doing here? Okay, so what I mean is just do layer by layer. Okay. So for example, uh, this layer here. This layer of this thickness. Okay. So the thing here is we need to find this one. Okay. So let's put our coordinate here. This is y. This is 0. This is 10. Okay. Okay. So here we have, so here we have, if we have something here, position y, for example. Okay, and you have a formula for a similar triangle. Triangle similarity. Okay, because we need this one here. Okay. So say this is the R, because it's radius. All right, so let's compute the let's this is the big triangle versus the smaller triangle. Okay, from this here they are similar triangle. So you have the ratios are the same. Okay, for example, the small time divided by this, so R over 4 is same as Y over 10. Okay, does this correspond to this one? This corresponds to the whole thing. Right, so R is, let's see, R is Y. Okay. All right, so this is uh, so this area, this volume, see, this volume is the volume is, let's see, delta V. Delta V is pi I squared, pi R squared. Okay, times this delta. Okay, that's the volume. Uh, so the force is, so we get, sorry, that's so delta is the density. So the work force is the density is delta. All right. So delta is the density of water in cubic uh, pounds per cubic foot. Anyway, it's denoted by delta. Okay. So the force is delta times. Let's go back to our calculations. Density as density. Okay. So the work not the whole is this part, delta times its volume, times distance traveled by this layer to go out. Okay, so this is the distance here. So if you have 10 here, or the whole thing is 10, and you have y here, so the distance traveled is just the rest of this. So it's 10 minus y. Okay, so you get this one times 10 minus y. Okay, so now we can compute uh, the work done by this force is approximately the sum. So delta phi 10 times 10 minus y. Okay, and what if this is equal? That means we take limit. So we take limit here. Okay. And y from y from 0 to 10. It's the populations plugged into your wolfram and then get the answer. Okay. Questions? All right, part B. Same situation, except that the pump here is that the 10 feet above the top of the tank. All right, so here's the situations. So if we have, this is 10, this is 0. Now the pump here is the 20. So this is the pump. So this layer, you're going to compute the mass, the force, and then pump it towards this. Okay. If this is y, this distance is 20 minus. Okay. So similarly, we get the work is, let's see. Okay. Exactly the same thing here. This is okay. Y from what to what? What's the bound for the integration? That's from y equals 0 to y equals 10. So everything's the same as this, except this difference. Position of the pump. Okay, questions? All right, just an
Sir, I have a
example.
question.
Yes, sure.
So wait, the distance is 20 minus y, but why do we take the integral from 0 to 10?
Because the water is, well, the bounds for integral based on this, right? Which one do you partitions? Are we partitioning this or this one?
The one inside the cylinder.
And just the water, right?
Yeah.
So just the tank, not the whole thing. Okay. So we're not partitioning this, but this one here from 0 to 10.
All right. Thank you, sir.
Okay. Other questions? Okay. I guess I'll stop here. Kak Kemal will uh, discuss with you the problems from this chapter. Okay, so mostly on this, how to revolve things, volume of revolutions, solids of revolutions, this work, center of mass. Okay, and while I will continue with the new chapter on log and exponential functions. So I'll continue with for the first half, probably 40 minutes, I'll lecture about the new chapter, and then afterwards you start with the tutorial with the Kakemo. Right? Okay, I'll see you then later. Thank you. I'll stop this.
Okay, thank you, sir. See you next time.
Thank you.
Thank you, sir. See you
Thank you,
next
sir.
time.